Good morning, everyone. I'm Tongxin, PhD student from Spacetime Lab UCL, and thank you for attending my talk. Today, I would like to share our work titled "The Exploration of Human Activity Zones Using Geo-tagged Big Data During the COVID-19 First Lockdown in London, UK." So to clarify the research interest of this study, here there are three parts. First, we aim to extract human mobility or activity pattern at high resolution geospatial and temporal units from geo-tagged big data. Apparently, such high resolution human mobility pattern is more valuable than the city or regional level migration data, such as the data sets from Google or Apple mobility metric. So second, based upon the definition of the urban function zones, we use human mobility. We use the human activity zones characterizing the dynamic fault force patterns of urban function zones. And further, given the controlling policy responding to the COVID-19 pandemic, HAZS will reveal significant insights of the policy impacts on urban places and the societies. So in our methodology parts, we use this analysis framework consists of 3 steps to extract the human activity zones. First, we use the raw mobile phone GPS data representing the geo-tagged big data to extract the stays or stops from single user approached by the activity detection algorithm. Here, one stays or stops is defined as someone spent some times in one specific places or areas. So the second, we aggregated the numbers of detected stays as the proxy of human activity metric to define the spatial and temporal units as the aggregated footfall numbers. At last, the human activity zones can be characterized by temporal footfalls at the defined urban areas using the agglomerative clustering methods. So our case study focuses on the MSOA level analytics and hourly level analytics in London metropolis, which is consists of 983 MSOAS, and our observation time period is from March the 9th, 2020 to April the 6th, 2020, which is 2 weeks before and after the first national lockdown. So we can get the human activity pattern resolution representation matrix, which is 983 MSOS and 1 month at hourly level. So here in this study, here one stays or one stop is defined as a user spend at least 5 minutes within 50 meters spatial radius from a given GPS trajectory point. So in this figure, this is an example of a user's stay points identified from GPS data, trajectory data. Here, the red rectangle represents one stay or one stop, and every and every state or every point stops are linked by the temporal orders within the whole mobility trajectory. So then in our observation time period, we get the daily user numbers and changes shown in the left figure. It denotes the devices has declined from about 260,000 to 140,000 after the first national lockdown in London. And in the figure of the daily identified human activities shown on the right, we can see the human activities also declined from about 1.5 million to 500,000 after the first lockdown. Obviously, such declined patterns may be caused by the stay-at-home order, which lead to the restricted citizens' routine activities in London. In terms of the temporal patterns of human activity, we can also get the similar decline pattern in hourly level regarding the human activities. However, while compared the before and after lockdown, it's still significant that the morning and the afternoon communication peak of a day in one day before lockdown, but such communication peak disappear during the after lockdown period. So in addition, the levels of the human activity tend to be stable after during the after lockdown period in London. So this is the spatial distribution of human activity at MSOA level in London. Here we use the sum of the footfalls to represent the human activity patterns at every MSOA in London. Here we separate our observation time period to 4 weeks. So overall, from the map legend, the footfalls are the sum of the human activity numbers. It tend to be declined when compared before and after lockdown. However, the comparatively, the busy areas before lockdown are still be busy after lockdown. So I mean, for example, the Heathrow Airport located at the west of London, and in the you can see the darker area in the 4 maps. And the city of London located at the center of London, and still quite busy. And in terms of the 4 weeks time periods. And however, the gap of the human activity level between busy and not busy areas tend to be lower than before. So, so the darker blue areas tend to be increased in the last 2 weeks maps. Then, in the step of the detecting human activity and rules, first we use evaluation index for identifying the optimal cluster numbers in our clustering methods. Here we use the coefficient index as the definition of the optimization. Here the index are measured by 3 different distances, and they are the Euclidean, Manhattan, and cosine, and all 3 types of the index are show the optimal numbers is the 7, and which we can see the 3rd point in in every subfigures. So we can get the seven clusters from the MSOS, which is the 7 types of the HAZS in London. So we can see the distribution of the HAZS in the map of London. This map show the quite significant levels regarding the HAZS. For example, the HAZ5 with the red color are mainly concentrated on the central areas of the London metropolis, and the HAZ6 with the orange color are mainly distributed with the outlier areas of the London. Here, this kind of distribution of human activity zones may strongly related to the urban functional features, such as the land uses, and the changes of human activity during the pandemic are significant different in terms of such 7 types of HAZS. So when consider the lockdown effects in hourly human activity patterns in the HAZS in London, here we select 3 types of HAZS to explain these effects. The red arrows, in terms of the before lockdown and after lockdown, we can see the communication peaks are all disappeared when compare the before lockdown and the after lockdown period. And actually, apparently is the City of London area, and the green areas represent which is another kind of the central areas in the city or in the London, also show the declined patterns of the human activity levels, and the disappear of the communication peaks. And when we take a look at the green areas, which mainly are connected to the green parks or the green lands, we can see even the communication peaks are disappear, but the levels of the human activity declined at a quite low level, and when compared the former 2 types of the HAZS. So further, if we take a glance of the specific MSOA, as we can here we select the City of London. So we can see it's kind of a huge and significant decline in human activities or the footfalls numbers. It's declined. It's declined dropped from the 4,000 to the 500 overall. So this kind of the change may be related to the maybe the City of London don't hold a lot of the residence areas, and its urban functional, which is the commercial functional areas, and the second is the Richmond Park. So we also can see the declines of the human activity levels, but the peak, the communication peak is not is not quite significant. And at last, we want to know the explanation of such changes in the HAZS distributions. Here, first we select the population density as the variable to test the statistical significance. And so here we use the we use the box plot to see the difference of the population density in 7 types of the HAZS, and the statistics shows is quite significant. And at last, we add other place features indicators, and these kind of the indicators are all from the Office of National Statistics. We can see the different place feature indicators are all significant in the 7 types of HAZS in London. So so we can get such types of HAZS generated from the MSOS are quite strongly associated with the social and economic variables in London. So the summary is first, the HAZS exhibit declines in human activities, which also caused the footfalls. Second, HAZS are strongly associated with urban land use and the population variables, and the social, economic, and demographic variables during the COVID-19 pandemic. And our work in progress consists of the detecting the human activity patterns at different geospatial units, such as the LSOA street segment and specific types of places, such as the public transportation stations, supermarkets, and parks. Second, further semantic extractions from mobile phone GPS data, such as the home location, work location, and the travel location. And at last, this kind of data or the human mobility metrics are not only useful for the pandemic period to identify the risky areas, but also used for the post-pandemic period. If we connected this kind of human mobility to the COVID-19 cases or some other death rate. So that's all. Thank you.
Well, some in the Q&A box. Sorry, can you? So this is from.
Okay. Is the question from William?
Yeah, that's right. So it says.
Okay.
In more detail, how you.
Okay. In our paper, we have acknowledged that this data source is from the location science, which is data company, and this data company have the academic collaboration program with our space-time lab, and the GPS, the raw GPS mobile phone data sets are extracted from different kind of the mobile phone apps. So what is interesting is that the collect time period from everyone's mobile phone is not regular but randomly. So in our state detection methods, we define the 5 minutes to extract the significant stops or the stays. So this method is quite strongly related to our data, the raw GPS data, and the last question is the privacy issue. Yes, we consider. Yes, we have considered the privacy issues addressed. So we don't analyze any individual level analysis in our study. So we aggregate our GPS data to the place-based analysis, and the data in our analysis are all protected by the DSH of UCL, which is a quite data protection system. So apparently it's not open source. Yes. Okay, so the next one, what apps use it to, and we defined the right. Okay, and this may be a little difficult because when we communicate to the location science, the apps are quite widely. I mean, maybe there are lots of about the travel plan apps, such as some maybe related to the quite similar with the city mobility or the Google Maps, and some are the transportation guiding or some entertainment apps. So it's quite it's kind of various and kind of the apps. So we'll do demographic. In terms of the demographic spread of the participants, sorry, we don't have the information of regarding this kind of variables, but we can get the platform is Android or the iPhone. Yeah, this just we can get. So do you, okay, so
okay, so this might have to be the last question.
Zhiqiang. Okay, so about the Zhiqiang's question, let me see, and the data is okay, thank you, Zhiqiang's question. We have tried the different kind of the temporal interval to define the stops. However, for example, we use the 1 minute or 2 minutes. However, as I have said, the GPS point is not collected regularly. So if we use 1 minute or 2 minutes, some of the points from maybe the train and travel are defined as our stops or stays points. So this kind of the parameter, I mean the 5 minutes is the human defined. So this just the initial processing of this data. So maybe in our further analysis, we will try the different time intervals and test the relation to another patterns. Thank you.